So in this question, we have an amusement park ride. We are told that it's rotating counterclockwise and has a constant speed v. And this is a circular body, so we should be thinking about centripetal acceleration. All right, so if the v is constant, and the radius is constant, the centripetal acceleration would be constant, all right? Points A and D represent position of a car at the highest and lowest points. Person FG sits upright in the seat, and when it passes point A, it exerts a normal force of 0.8 Fg. While passing point A, the person releases a small rock of mass m, which falls to the ground without hitting anything. So a little rock is dropped. So what describes the passenger's linear and angular velocity while passing point A? Well, the linear velocity at point A is directed tangent to the circle, like so. And they're using velocity, so direction matters. All right, and the angular velocity, which would be omega, has, let's see, is a, so the linear velocity has a magnitude. Let me just drop back to that, and a direction. The magnitude remains the same, but the direction changes, which suggests then that the velocity is changing. The omega has a magnitude in a direction, and we are told that it's constant speed v, which means during equal intervals of time, the constant angle, delta theta over delta t, so the angle's changing the same amount every second, so the magnitude remains the same, and the direction is defined as the angular direction, which is also the same. So what we think is happening to the linear velocity is that the linear velocity is changing because the direction is changing. So that's out. So that leaves choices C and D. And if we look at the angular velocity, we think it's constant because both the magnitude and the direction remains the same, and therefore choice D.